I'd like to work the two problems that I gave at the end of Lecture 10, Part 1. So the first problem is, what is the acceleration of gravity at the International Space Station? And to do that, we use the fact that the force of gravity is G times m1, m2 over r squared. And in this case, one of the masses is the mass of the Earth, the other is of the International Space Station, and this is going to equal the mass of the International Space Station times the acceleration at the International Space Station. So I'll call it 2. So the ISS is object 2. And so we get that G m1 m2 over r squared is equal to m2 a2. We want to solve for a2, so we just cancel the m2's for the International Space Station mass on both sides. And just because it's on both sides, we can divide through by it, right? 1 over m2 times 1 over m2, and I do that to get a2 by itself. And so that's G m1 over r squared. And remember, draw a picture because otherwise you might make a mistake about what r is. So here's radius of the Earth. Here is the altitude or the height. And here's the International Space Station. So the radius from the center of the Earth to the International Space Station orbit is radius Earth plus height. And so I can plug in G mass Earth over radius Earth plus height squared. That's r squared. And then I can plug in, and this is the height of the International Space Station, so the height of object 2. And so G is the 6.67 times 10 is negative 11 Newton meters squared per kilogram squared times m1, the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. I'm reading that from off camera. I do not know the mass of the Earth offhand. And I'm dividing by radius Earth in meters, right? Because we want to cancel 1 power of meters up here. So we don't want to do kilometers. Radius of the Earth is 6,380 kilometers times 1,000 meters per kilometer plus the height of the International Space Station, which is 400 kilometers times 1,000 meters per kilometer, and the whole thing squared. And if we plug that into a calculator, we come up with the 8.66 meter per second squared. And I'll just pause for a second and calculate to double check that. And yes, it works out. And I did I made a calculator error, so because I was doing part of it in my head, I made a calculator error. Yeah, just make the point, mistakes happen. But I wound up with, actually, it's a good story because I wound up with 8.66 million meters per second squared. And I knew that that was incorrect because the acceleration of gravity on the surface at the surface of the Earth is only 9.8 meter per second squared, so it wouldn't make sense for it to be 8.66 million meter per second squared anywhere, let alone away from the surface of the Earth, where it should be a little bit less, and this is a little bit less than 9.8 meter per second squared. Of course, if you go far enough away, it'll be a lot less. But the International Space Station is not that far away in terms of the change not that far away relative to the radius of the Earth. And so the difference between its acceleration due to gravity and the acceleration due to gravity at the surface of the Earth is not big. It's the difference between 9.8 and 8.66 meter per second squared. So number 2, at what altitude does a satellite pass over the same country twice a day? So altitude at which a satellite passes over, when I say the same country, some countries are quite big. I'm just thinking of it passing over Russia, for example. It could be, really, what I'm asking here is passes over the same spot. And actually, that's problematic too, because with the Earth's rotation, it's a bit tricky. So what do I actually want to say here? Yeah, my point was to calculate roughly the altitude at which the period would be 12 hours. So passes over the same, I'll keep it country. Altitude at which satellite passes over the same country twice a day is equal to what? And you got to keep in mind that this is a rough figure, right? Because depending on the country, you could the period could be off by a significant amount if the country is very big. But my point is, you can estimate this altitude by saying that the period is 12 hours. That's the simplest way to proceed. I think that the question is asking clearly for a rough value because it says country. It doesn't specify all sorts of complications like what to do with the Earth's rotation and all this sort of thing. So roughly the period is 12 hours. And so using the same method, and so you could just, if you have the work from the previous problem, you could have just plugged this in and gotten an answer. But from the example in the lecture, but I asked you to start from scratch. So that's what I'm going to do. So we have, we draw the situation. Here's radius of the Earth. Here's the orbit of the ISS. Here's the height, the altitude of the orbit. And so the radius of the orbit is r, where r is radius Earth plus height. And that point I keep making because it comes up in these problems. And we want to find the altitude, right? So what we're going to do is we're going to draw the free body diagram. And this is the ISS. The only force on it is the force of gravity due to the Earth. And that force points towards the center of the Earth, so it points in the radial direction. So the sum of the forces in the radial direction is equal to the force of gravity. And that equals the centripetal force, which is, I'll say centripetal force. And so you get force of gravity, which is G, mass Earth, mass International Space Station, which I was calling 1 and 2 in the previous problem. I'll call them Earth and I here, divided by r squared is equal to the centripetal force on the thing that's moving in the circle, which is the International Space Station. So the centripetal force is the mass of the thing that's moving in the circle, which is mass ISS, times v squared over r for the thing moving in the circle. And so you solve, we want to solve for the height. So that means we want to solve for r and then use this equation to get h, just as we did before. And so I want to solve for r. So I'm going to multiply by r squared on both sides, and I'm confused. Oh, right. I need to, yes, I need to replace v because I know the period, I don't know the speed, right? So v is the circumference, it's the distance traveled, which is the circumference, 2 pi r, divided by the time taken. So distance over time for constant velocity is 2 pi r over the period. And yes, and so then I get that g mass Earth mass ISS over r squared is equal to 2 pi, um, let me do it, 2 pi r over the period, which is v, and that's squared, times 1 over r. And I'm going to simplify g mass Earth mass ISS over r squared is equal to 2 pi over period squared, right, that's this, times r squared over r, which is just r. Then I multiply by r squared on both sides to get eventually r by itself. So, and I'm going to multiply by the reciprocal of this thing on both sides. So times t over 2 pi squared. So times t over 2 pi squared. And so that gives me, this cancels, and I get the r squareds cancel, and I get g and mass Earth. Oh shucks, I dropped the mass of the International Space Station on the right, because I was going to cancel it eventually, so I dropped it. Okay, and so then mass International Space Station cancels. Get rid of that. It can't affect the answer because it doesn't matter what you put at a given radius. It's going to need the same speed to get round. But anyway, this is why that's true, because the centripetal force equals the gravitational force, and so the masses of the thing that's in orbit cancel. So you get g mass Earth times t squared over 2 pi squared, which is 4 pi squared. And, right, g mass Earth, t squared over 4 pi squared. And that equals r cubed. And then I take cube root of that. So I get r is equal to g mass Earth, t squared over 4 pi squared to the 1/3. And that equals g, which is 6.67 10 to the negative 11 Newton meter squared per kilogram squared. It's an 11 times mass Earth, which is the 5.97. Help me, I almost know the number by now after a few times. Times 10 to the 24th kilograms times that period squared. So the period is the 12 hours times the number of seconds per hour. So it's 60 minutes times 60 seconds per hour. So 3,600 seconds per hour. And that is squared. The whole thing is to the 1/3. And divide that by 4 pi squared. And I will plug that into the calculator. and see what I come up with. It's going to come out to be 20,200 kilometers. I should really round that to 20,000 since it's an approximate thing with you know, a country which could have some which has some uncertainty as to where as to the size of it, whether you've actually gone around the two orbits. So one moment, I'll be back. So I recopied, I copied the algebra because that was getting messy. And so this was equation 2, which we started with. Cancel the mass of the International Space Station on both sides. Plug in v is 2 pi r over t, and then just simplify to get this. If you have any problem with this, I mean, if you didn't come up with the right answer, please you know, come by office hour and talk to me. I'm happy to look it over. And so I made a calculator error. I forgot to square pi when I divided, and therefore I was off by a factor of pi to the 1/3. And so when I corrected it, I got this. And the answer then, this is r. Remember that r is radius Earth plus the altitude, the height. So if I subtract the height from both, I'm sorry, if I subtract radius Earth from both sides, I get that the height is r minus radius Earth, which is 26,600 kilometers minus the given radius of the Earth, 6,380 kilometers. I'm going to round it to just the 1 sig fig. If I subtract 6,380, I get 20,220 kilometers. The answer I gave in the lecture 10, part 1, was 20,200 kilometers, but I'll round it to just 1 sig fig, 2.0 times 10 to the 4, I'm sorry, 2 rather. 2 times 10 to the 4th kilometers, or 20,000 kilometers. And that way I don't claim greater precision than I would have by, given that I've defined the problem so loosely, the same country twice a day. Yeah, I was hoping to avoid complications in doing the problem. I just wanted to replace the 90-some minutes of the International Space Station with 12 hours and solve the problem that way. So yeah, so that's that answer. The first part, the answer was 8.66 meter per second squared. And remember, the astronauts do have a non-zero weight if you define weight as the force of gravity due to the Earth. But they're in free fall, and so they float around, and they're apparently weightless. So, well, thanks for your time, and I hope this was useful. And until next time.